In this video, we will derive the relation between the Young's modulus and the modulus of rigidity. So, Young's modulus, the notation is E, and the modulus of rigidity, the notation we are denoted by G here. So, what do you mean by Young's modulus? We already general formula how we will get the Young's modulus. That is, if the body is subjected to any tensile or compression load. Suppose, for example, if body is there, if it is subjected to axial tensile load F, obviously it will undergo certain deformation. That is certain deformation. Okay. So here in this case, it will go different. The variation of loads while applying the load, it will undergo variation of stresses here. Okay. So within the elastic limit, the stress is directly proportional to strain. Okay, that we know already the basic formula. Within elastic limit, the stress is directly proportional to strain. Okay, this is stress, this is strain. As the stress goes on increases, the strain will goes on increases here. So if you want to remove the proportionality constant, this will be equal to E into strain, where E will comes the Young's modulus or modulus of elasticity. So obviously E equal to Young's modulus equal to stress by strain. This is how we will get the Young's modulus. This is related to the axial loads, tensile load or compression load. You will get this constant. E is the constant in this case. Then next one more word here, modulus of rigidity. Modulus of rigidity, it is denoted by G. Where we will get the G here? If any body it is subjected to the shear load or shear stress. Suppose, for example, this is the block is there. It is one end is fixed, and other end, if you apply the load, obviously it will changes its shape. It means here it will changes the shape. So here you are applying the shear load. It is slipping load. In this type of loads, you are getting the stress shear stresses. So here, as usual here, if the body is undergo any shear load or shear stress within the elastic limit, the shear stress, whatever the shear stress, is directly proportional to the shear strain. Shear strain is denoted by the gamma here. Okay. So if you want to remove the proportionality constant, shear stress equal to G into shear strain, where G is the modulus of rigidity. So what I mean total, E always will comes whenever the body undergo tensile load or compression load. In that case, you will get this constant, E constant, Young's modulus. Whereas G or modulus of rigidity will comes into picture whenever a body will undergo a shear type of loads, shear stresses, shear loads or slipping loads. One end is fixed, other end is the applying the shear load. Okay. So now today we will derive the relation between E and G, Young's modulus and modulus of rigidity here. Okay. We will go step by step. First, consider a square block. Consider a body, it is in square nature, ABCD, and its one end is fixed, AD is fixed, whereas the BC, the face BC is subjected to shear load. Okay, and its thickness is unit thickness. We need to consider as the unit thickness. Okay, I will write, consider a body ABCD. It is normally we have taken it as square with thickness, unit thickness, and its one end is, its end AD is fixed, and the face, this is the face AD, is fixed, and the face BC is subjected to shear force, because it is slipping in nature, so it is shear force. Shear force F tau. Okay. What is AC? AC is diagonal. AC is diagonal. AC is diagonal of ABCD. Okay. Now, if we applied a shear load on the face BC, what will be the changes in the body? The point B and C, it will change its shape, but AD, they won't change its positions here. Okay. So after applying the load F tau, the new point here you will get B dash, and here you will get C dash. Okay. It means the face, it will be changing here. This is B dash, and this will be C dash. This will be C dash, where AD remains same. AD remains same. Next, after applying load F tau on face BC, the points B and C changes their position, to B dash and C dash, Okay. B will change to B dash and C will change to C dash. Okay. Now we will get one more diagonal, that is AC dash, right? After changing its shape, we will get the new position, that is AC dash. The new diagonal is AC dash. Okay. Now draw a line. You just draw exactly this point P. From C, draw a line perpendicular to AC dash, which meets AC dash at P. Okay. From C, you need to draw a line which is exactly perpendicular to AC dash. It means this is 90 degree. AC dash, which meets the diagonal AC dash at P. Okay. Just I'll write next point. From C, draw a line perpendicular to what? AC dash. Perpendicular to AC dash, which meets AC dash at P. It means you need to draw a line CP perpendicular to AC dash. CP perpendicular to AC dash. Okay. So now here the angle PCC dash is 45 degree. Okay. This angle, whatever we are getting here, this will be 45 degree, and this is C. Okay. 45 degree, and this point is C. Because the strain is very less After applying the load, the strain whatever you are getting PC dash, it is a change in length that is very less. So obviously this angle PCC dash will be considered as the 45 degree. This angle is 90 degree, this 45 degree and this 45 degree. Okay, just I'll note down here angle PCC dash equal to 45 degree, since the deformation is considered as very small, is considered as very small, very small. Okay, these are all the data. Now we should start to prove one by one here. Okay, see, this is AC is original diagonal, AC dash is of the diagonal after the deformation, Now we will get the strain. Strain means we know that change in length divided by original length. How much it will be change in length in the diagonal? It is the change in length will be PC dash, because AC equal to AP. Will you agree? From figure AC equal to AP, because CP is perpendicular. AC equal to AP. Okay. So now strain of diagonal AC, because AC will undergo certain change in length after applying the shear force. Okay, that will be equal to, just I'll write strain of AC. What is the general formula? Change in length divided by original length. Just I'll write here change in length divided by original length. Now apply these with respect to this diagonal. If I apply here, this will be equal to change in length, just I'll write AC dash minus AP, right? How much it goes? That one. AC dash minus AP, okay, divided by this much change in length, divided by original length is how much? AC. Your original length is AC. Before before applying any load, AC is the diagonal. So original length is AC. So this all is related to only these two diagonals. Okay. Change in length AC dash minus AP, whatever this much you are getting, divided by original length is AC. This I can write it as AC dash minus AP is PC dash, right? PC dash. This I'll write it here. This will be equal to PC dash divided by AC. Original length is AC. Okay. This is strain of diagonal AC. That is strain of diagonal AC. Call this one as equation number A. Okay. Now we will find out one by one PC and AC. Okay. Then we will substitute here. First, to find PC, for PC dash, this is PC dash, right? Now we need to consider a triangle. Which triangle? PCC dash. That is right angle triangle. Okay. We need to consider a right angle triangle PCC dash. Consider a right angle triangle PCC dash. Okay, here 45 is there. Okay, sine 45. I'll take sine of 45 degree equal to, why I'm taking sine of 45 degree? Because I want PC dash, right? PC dash is related to sine quantity, and it is 45 degree. Sine 45 equal to opposite by hypotenuse. Which one is opposite here? this is PC dash, right? Opposite is PC dash. Opposite side divided by hypotenuse. Which one is hypotenuse? CC dash, because this is perpendicular. These two are perpendicular. This will be adjacent side. CP is adjacent side. Okay. PC dash is opposite side. CC dash is adjacent side. Okay. So sin 45 equal to opposite PC dash divided by hypotenuse CC dash. CC dash. Okay. Therefore, I want PC dash, right? PC dash. PC dash equal to sin 45. Sin 45. What is the value of sin 45? 1 by root 2. 1 by root 2. So I'll write just sin 45 into CC dash. CC dash. Okay. Into CC dash. This I'll write it as sin 45 is 1 by root 2. Right? 1 by root 2 into CC dash. CC dash. This is PC dash. PC dash. Okay. PC dash. Now come to the AC. AC. Where is AC? This is AC, right? We need to consider a triangle ACD. ACD. Okay. For now I'll write here for AC. For AC, consider a right angle triangle ACD. ACD. Okay, because I want AC, so that's why I consider a triangle ACD. In this case, AC square equal to AD square plus DC square. Pythagoras theorem. AC square equal to AD square plus CD square. Right? AC, therefore AC, I want AC equal to square root of AD square plus CD square. Okay? This will be equal to square root of AD. AD is equal to CD, because I said this is a square. This is a square. In the beginning, while writing the points, I wrote the body A, B, C, D is a square. Is a square. Therefore, can I write it? AD equal to CD. AD equal to CD. This I'll replace CD square plus CD square, because AD equal to CD. AD equal to CD. Okay. AD equal to CD. How much I'm getting here? That is, this will be equal to 2 CD square. Square root of 2 CD square. This will be equal to square root of 2 CD into CD into CD, right? Into CD. This is the value of AC. Now I found AC. I found PC dash. I found PC dash. Okay. Now substitute these two values in equation A. In equation A. Okay. Therefore, equation A becomes substitute PC and AC. PC dash and AC values in equation A. In equation A. Therefore, equation A becomes I'll write strain of AC, diagonal AC, strain of diagonal AC equal to, what is PC? PC dash. That is PC dash, right? This is PC dash. PC dash is CC dash divided by square root of 2. CC dash divided by square root of 2 into 1 divided by that is divided by AC. AC is 1 divided by AC value is square root of 2 into CD okay. This after simplification, how much you are getting? CC dash divided by CD into 1 divided by 2, right? 1 divided by 2, because square root of 2 into square root of 2 is 2 here. Now CC dash divided by CD, CC dash divided by CD. From figure we'll check. Strain of AC. From figure CC dash divided by CD. Now we will come to the shear strain word here. Shear strain bit. Shear strain, just I will write here shear strain. What do you mean by shear strain? I will define here. This is normally denoted by gamma. Okay, gamma, that will be equal to gamma, that will be equal to, see, when a body it is subjected to shear stress, it will undergo certain deformation. Whatever it is going, the certain deformation, C dash or B dash, both are same with respect to original. This is AD is constant, it is not changing. So here it will make certain angle of gamma. This is called shear strain. It means the shear strain is the gamma, this angle. So this I denoted by normally tan of gamma, that is general formula. I am explaining here, that is tan of gamma equal to opposite by adjacent side, because this is 90 degree, opposite is CC dash divided by adjacent side is CD. This is the definition of shear strain. Shear strain is nothing but tan of gamma after undergoing the phase BC to B dash C dash with respect to original AD phase, it makes at an angle of gamma. So tan of gamma is opposite by adjacent side. That is the definition of shear strain. Okay, shear strain. Now the gamma is very small. Whatever the deformation, it is very small. So normally we are taking tan of gamma is gamma. Since gamma is very small, tan of gamma is nearly equal to gamma. Therefore gamma is equal to CC dash divided by CD. This is equal to shear strain. Okay, this you need to remember before deriving. This is the definition of the shear strain. So from the figure, CC dash divided by CD, can I write it as gamma? It is shear strain. From figure, CC dash divided by CD equal to gamma, shear strain. Therefore strain, substitute. Therefore strain in diagonal AC equal to, how much we are getting here? Gamma shear strain divided by 2. Call this one equation as B. Okay. Now when a body is subjected to shear force F tau, this diagonal AC, whatever the element of the diagonal AC, it will undergo the tensile stress and compression stress. That is, I will just write it here. This is the body. ABCD. This is A, B, C, D. So this is the diagonal. When it is subjected to shear force F tau here, it will undergo a normal forces sigma 1, here tensile stress sigma 1, and in opposite phase it will undergo a compression stress sigma 2. Okay, please concentrate here. When it is subjected to shear force here on the face BC, here in the AC, its effect is in AC it will undergo like this, the normal stress. This is the tensile stress sigma 1 and sigma 2 along the AC, and in the opposite direction it will undergo compression sigma 2 and sigma 2. Okay, so these are equal to shear stress tau. Just I'll write here, when diagonal AC, when phase BC is subjected to shear force F tau, diagonal AC, the element of diagonal, the element, this is the element of diagonal AC is subjected to tensile stress sigma 1 along AC, and subjected to tensile stress sigma 1 along AC and compression stress in opposite phases. See, please concentrate here. The effect of F tau on diagonal AC I drawn here. I drawn as the element. By taking the element, I drawn. In this way, it is undergo tensile, and in opposite direction, it will undergo compression. And these forces will be equal to shear stress, because it will here also it will undergo shear stresses, and is equal to shear stress tau. This I will keep it as equation B as it is. Therefore, can I write it as sigma 1 equal to sigma 2? Sigma 2, it is minus sigma 2 equal to shear stress. Okay. Now, only by considering the normal stresses sigma 1 and sigma 2, we need to write the strain formula. I will write the strain in AC, because strain in AC we are dealing with the diagonal AC. Strain in diagonal AC equal to, what is the normal formula? In the previous video we used so many times. So stress by E, right? Sigma 1, just I'll write with respect to tensile, plus that is sigma 1 stress by E, right? Stress by E minus in opposite direction, minus because it is compression, minus sigma 2 by E. Okay, into nu into, this is nu into sigma 2 minus nu into sigma 2 by E. Okay, stress by E minus, this is in opposite phases, minus into nu into sigma 2 by E here. Okay, this will be equal to what happens, sigma 1 by E minus into minus plus nu into sigma 2 by E. Okay, so what I wrote here, these two, sigma 1 or sigma 2, both are equal to shear stress. Can I replace sigma 1 and sigma 2 by shear stress? This I'll write it as shear stress divided by E plus nu into shear stress divided by E. Now remove the common factor. This will be equal to, I will remove shear stress divided by E as a common 1 plus nu. 1 plus nu. This is strain in AC. Strain in AC. Call this one as equation number. Call this one as equation number B. Equation number C. Okay. So now here in B we derived. We can compare these two. But before dealing B, just I'll elaborate little bit, explanation, a little bit simplify here. We know that the one more formula, we know that here, what is modulus of rigidity? G. G equal to, that is modulus of rigidity, equal to G, right? G equal to, what is the formula? Shear stress by shear strain, right? Shear stress by shear strain, that is shear strain. Okay. Therefore shear strain from this, how much I am getting here? Therefore shear strain equal to tau by G, right? Tau by G. Now substitute this shear strain here, then make it as equation B. Okay, just I am still simplifying here. Substitute this shear strain here. Therefore here how much I am getting? Therefore strain in AC equal to, what is shear strain? Tau by G divided by 2, into 2, into 1 by 2, that is into 1 by 2. Now this call it as equation number B before. Okay, this is equation number C. Now can I equate equation B and C? Because strain in AC. Now equate equation B and C. What is B here? Tau by G 2G. Tau by 2G equal to, here tau by E into 1 plus nu here. Okay. Now cancels any matter. This one equal, cancels here. Therefore E equal to, from this one, E equal to 2G into 1 plus nu. Right. This is the final formula. This is the final derivation. We are derived the relation between, the headline is the relation between Young's modulus E and the modulus of rigidity G. Remember, always E equal to 2 times G into 1 plus nu. This is the final formula we are derived here. Okay.